Welcome to phase diagrams. So here we're looking at a phase diagram of a typical substance, a generic substance. So down here we have the temperature axis, here we have a pressure axis, and then we've got some lines in here. And you can see that we've got labeled some various places. We've got over here, we've got a region that is a solid phase, here we have a region that's the liquid phase, and here we have a region that's the vapor or gas phase. And so at very low pressure and high temperatures, we have a gas. If we keep the pressure constant and we lower the temperature, then we're moving this way. At some point, we reach this curve. And if we, on the other side of that, we have a liquid. So this curve is the vaporization curve or the condensation curve. So this is the vaporization curve. If we keep going, now we have a liquid, and at some point then, we keep the same pressure. We then transition to the solid phase. This is, of course, our melting curve. We're melting if we go this way. We're freezing if we go that way. So this is our melting curve. Now, we've got two other points. We've got this point down here labeled with a T, and that point up there labeled with a C. This is the triple point at which we have the solid, liquid, and gas phase all existing at the same temperature. There's only one point that occurs at. And up here we have the critical point, and I'll get back to that in a minute. So you should see that we have the vapor pressure curve, the sublimation curve. The vapor pressure curve is the vaporization curve here. So this tells us at some temperature what the vapor pressure is at that temperature. The triple point is again that point. The critical point is this point up here. Now note that this curve continues going up for a while. It may go up indefinitely, it may not. At this point, this curve stops at the critical point. So this here is the phase diagram of carbon dioxide. So here for carbon dioxide, the triple point is at 5.11 atmospheres. At 1 atmosphere, carbon dioxide will sublime at negative 78 degrees Celsius. So note that now we're down here in a sublimation curve. So there we're going from the solid phase to the vapor phase, which is why at 1 atmosphere, so if it's exposed to air at normal pressures, then carbon dioxide just goes directly from the solid phase to the gas phase. It sublimes. This is why we call it dry ice. If you go get dry ice from, say, a grocery store, it boils at negative 78 degrees Celsius, so it's pretty cold, and it doesn't form a liquid until we get to a temperature of, or a pressure of at least 5.11 atmospheres. At any pressure below that, the liquid phase just doesn't exist, no matter what temperature we get to. And up here past the critical point, again, this line ends, this line continues going up, but this line ends because there's some pressure and some temperature at which we no longer have a liquid phase. So remember that this is the vaporization curve, right? Now, for vaporization to occur, we have to be able to break the intermolecular forces that are existing in our liquid. Well, at some point, the average kinetic energy of our molecules is high enough that basically all of our molecules have enough kinetic energy to break the intermolecular forces no matter how high we increase the pressure. No matter how tightly we squeeze those molecules together, they have enough kinetic energy to break those bonds. And when that happens, we've now reached the critical point, or we're above the critical point in terms of temperature. And so at any point from here over, the liquid can't exist because the molecules have too much kinetic energy. You can't condense the liquid out no matter what happens. And also what happens at the critical point is that at that point you now have a gas phase, because it's usually at a very high pressure. You have a gas phase that's very, very dense. The density of the gas phase is the same as the density of the liquid phase because it's a very, very high pressure gas. But that now means that if the density of the liquid and the density of the gas are the same, you essentially don't have two different phases anymore. You just have one phase. It's just a fluid phase. And so we call this, up here, we call this a supercritical fluid. Supercritical, meaning it's super above the critical point. It's a supercritical fluid. It's a fluid because it's a fluid phase. It's able to move, unlike the solid phase is. But essentially, there's no differentiating between a liquid and a gas phase anymore. It's essentially the same. So remember that a liquid phase is, by definition, more dense than the gas phase is. But if it's not more dense, if it's the same density, then there's really no difference between them. It's the same substance, it's the same density. You're not going to have the liquid phase condense and then sink and fall out like you do, say, liquid water falling out as rain condensing out of the atmosphere. If the atmosphere was really, really dense, so that the water vapor had the same density as the liquid water did, then the liquid water wouldn't fall. It would float in air. Now that doesn't happen because the critical point of water is significantly higher than 1 atmosphere, as the critical point of CO2 is also higher. But one more thing I want to point out here is that if you look here at this curve, at the melting curve, let's say we take liquid carbon dioxide at some temperature, right? It doesn't matter what the temperature is, but it's at some temperature. If we increase the pressure, we're going to move up. We're going to keep the same temperature. So we're going to move up on this line. Well, at some point that line intersects the melting curve. And that means that if we increase the pressure on liquid carbon dioxide, at some point we'll get it to solidify. Now that happens because this curve, this melting curve, has a positive slope. It leans this way. But now let's look at water. This is the phase diagram for water. And you notice this curve has a negative slope. It leans that way. Which means that if we have a solid water, so ice, and we increase the pressure, at some point the ice melts and turns into a liquid. Not the other way as for carbon dioxide. Now, carbon dioxide is the way that most substances are. Most substances have a positive melting curve here. Water is very special. Right? There are a few substances that do this, and water is by far the most common. Now, what this means is that you're able to then exert pressure on solid ice and get it to melt into liquid water. Well, this is one of the effects that allows us to go ice skating. Because as you go ice skating, you have your weight, your body weight, is being exerted downwards on the ice. But you're not on shoes, you're on ice skates. Now the ice skates have a very, very small surface area, which means the pressure is very, very high. And what that does is it allows a very, very thin film, because this only really works at the surface of the liquid. Well, I mean, this effect will occur, but you have to get to really, really high pressures to melt the bulk of the solid. But at the surface of the solid, you can do this much, much easier. And so right at the surface, the first atomic layer or two, you're able to have your ice skates increase the pressure enough to form a liquid layer. And now, instead of having your steel ice skate on top of solid ice, now you have the steel ice skate on top of water that's then on the ice. And that water is much, much slipperier, and that then allows you to go ice skating across the surface. Now note that the rest of the diagram has essentially the same general trend. We've got a triple point of water, we've got a critical point. The triple point of water is at 273.16 Kelvin. So, again, for the critical point, as a gas is compressed, the molecules become closer together. At some point, the pressure becomes high enough and the molecules are close enough to cause condensation to a liquid. But if we continue to increase the pressure, so down here, for water at 374, which is the critical point of water, 374 degrees Celsius, and 1.655 times 10 to the 5th torr, or 217 atmospheres. So really high pressure. We get water to its critical point. At any temperature above 374 degrees Celsius, you can't get liquid water to occur no matter what pressure, even if you go above 218 atmospheres, 217 atmospheres. But at that pressure now, we get our supercritical water. So the highest temperature at which a liquid phase can form is what we call the critical temperature, and the pressure that's required to form a liquid at that critical temperature is what we call the critical pressure. And above the critical temperature, the kinetic energies of the molecules are greater than the attractive forces leading to the liquid state, so we just can't get a liquid to form at all. And so at temperatures greater than the critical temperature, and at pressures greater than the critical pressure, the liquid and gas phases are essentially identical. Their densities would be the same, and the phase is called supercritical fluid. So that was phase diagrams.